right, so here we go. So problem number 16 on worksheet 3.4 is all about air resistance. All right, so before we dive into number 16, a couple quick things. So first of all, well, here, let me read through the problem. I guess we don't. Okay, so what do we know about air resistance? So in daily life, we sort of don't notice air resistance that much, right? Like when you're walking down the hall, you're not like, oh my God, there's all this air resistance, right? It's not like walking through a swimming pool where you're like, right? And there's actual water resistance there, right? Because the water is dense and it's harder to move. The air is pretty light, it's easy to move, right? Okay? But there are times when you're really conscious of air resistance. So can you give me an example of a time when you're really conscious of the air resistance? Sure, yeah, Dustin. Okay, cool. When it's super windy, because the air is moving. All right, for our class, we're going to always assume that the air itself is stationary. But I like the, and you're running, right? Because what's the difference? This is a dumb question, but bear with me. What's the difference between walking and running? You're going faster. You're going faster. It turns out the air resistance depends on speed. Oops, I wanted to grab one piece of paper and I grabbed two. Check it out. Here is a piece of paper. So first of all, if it's not moving, there's nothing to resist. So there is no air resistance. All right? Now, if I move this way slowly, watch the paper. See how it moved a little bit when I started walking? That's because the air resistance was pushing it and causing it to slant backwards. Okay? Watch what happens if I move really quickly. It moves a lot, right? More air resistance. There's more force on it, causing it to tip more. Cool? That's a big, important idea. Let's write it down. The faster an object goes, the larger the force of air resistance is. Big, important idea numero uno. If you did not know that, if that is not intuitive to you, please write it down and put giant arrows and smiley faces and unicorns and rainbows pointing at it. It is important. If you have highlighters, use your highlighters. My tea is very hot. Try to cut myself down to 1 cup of coffee a day. So I won't make that joke. So I'm drinking tea when I'm done with my coffee. I don't know if it's any better, but that's what I'm doing. All right, everybody good up here? All right, so another thing we need to make sure that we address is the direction in which the air resistance acts. Which again, for many of you is obvious, but maybe not for all of you. So notice, if the paper is moving that way, which way does the paper get pushed? The other way. If the paper moves this way, which way does the paper get pushed? The other way. So which way does air resistance act? Opposite direction of the velocity. Very similar to friction, right? Air resistance acts in the opposite direction of the velocity. I've gotten into making my exclamation points from the bottom up. You ever done that? Try it. Instead of this. I don't know, this is maybe more emphatic, but this. Uh-oh. Oh, man, I just disproved my point. Never mind. Experiment. I want a full report next Monday. All right. Everybody good with this? Air resistance goes in the opposite direction from the velocity. All right. A couple other things. When you jump out of a helicopter or off the roof of a building or something, what direction are you always moving in? Down, yes? And that means that the air resistance is always up, right? Now, hopefully, if you choose to do this, jump out of an airplane or a helicopter off the roof of a building, you will bring with you a parachute. Hopefully you'll have it securely strapped onto you before you do. When you pull the parachute, when you pull the cord, the ripcord thing, and the parachute goes poof, you do not go up. Okay? In the movies, sometimes it looks like, oh, they opened the parachute. They went up, right? But you don't. You do not go up. Here's what's happening. When they record that in the video, so here's our action hero, Vin Diesel, right? He's just jumped out of an airplane. So here's Vin Diesel. He's falling, right? And you're watching him, right? So there's the screen, and here's Vin Diesel in the middle of it, right? Somebody is shooting that footage. Over here, there's a cameraman, right? So think about what's happening. They're both falling, right? When he pulls the ripcord, the parachute opens, and what happens is he slows down, but our cameraman has not yet pulled his parachute, right? So think about what's happening. So they're both falling quickly, right? When they pull the parachute, what happens is he keeps falling faster than he does, right? So relative to my cameraman, didn't he go up from the cameraman's standpoint? Okay, but he's not actually going up. It's just from the perspective of the cameraman, it looks like he's going up. Does that make sense? All right, so you don't actually go up. All that's happening is you're moving slower than somebody who doesn't have the parachute open, and so relative to them, it looks like you're going up, but you're still going down. I did not do a great job explaining that. Did that make sense, though, despite my muddling through that? Raise your hand if you're confused about. Okay, so when you open the parachute, you're still moving down, just not as quickly. Good? All right, I believe that we have created all of the groundwork that we need to do to run through number 16. Are there any questions before I begin? Going once, twice, sold. All right, here we go. Number 16. No. Ha. Number 16, here we go. Kabam. A. Let's see, so what's going on here? We'll read through the problem. So it turns out that in the real world we have air resistance. This air resistance depends on the shape of the object, which is why this piece of paper, which is not crumpled, falls very slowly, and this piece of paper, which is crumpled, falls very quickly. More air resistance, less air resistance. Good? So it depends on the shape of the object and the speed of the object, which we already talked about. It always acts in the opposite direction the object is moving in. So suppose Roy, who has a mass of 80 kilograms, drops out of a helicopter which is hovering in the air. A, when he first drops, there's no air resistance. So what's his acceleration? I'm going to go through this. Here we go. Here is Roy. My board needs to be calibrated, so my drawings are going to get increasingly sloppy. He's got a mass of 80 kilograms, so we can find the force of gravity, right? So you just do 80 times 9.8, which gives you negative 784 newtons. Everybody good up to there? All right. What's his acceleration? Well, if that's the only force, then the net force is negative 784 newtons. So I can find my acceleration by doing net force divided by mass, and no big surprises, you get negative 9.8 meters per second squared. Okay? And the idea there is his initial velocity is 0, so there is no air resistance at the beginning. Cool? Questions? All right. B. Where's my sheet? I just lost it. Oh, I set it on the stool. Here we go. B. After about 3 seconds, Roy is moving down at 27 meters a second. So that number's made up. This important thing there is he's moving with some significant velocity. He's moving kind of fast. At this instant, the force of air resistance is about 144 newtons. Find his acceleration at this point. All right, so my drawing for B, oh, darn it, that's not what I wanted to do. So my drawing for B is going to look like this. So here's Roy. All right, let's see. So the problem told us the air resistance is 144 newtons. Which way is the air resistance going to go? Up, against the motion, right? So here's my force of air resistance. 144 newtons. All right, what about gravity? How do I find the force of gravity? His acceleration is not 9.8 anymore. So what do I do? Yeah, sure. Yeah, yeah, sure.
It stays the same, so it's just the weight. This weight isn't much.
Good. Yeah, remember, force of gravity is weight. The equation for force of gravity is not mass times acceleration, it's mass times acceleration of gravity. The acceleration of gravity on the Earth is always negative 9.8. It's not the same as the acceleration of the object. This is what I was talking about when Ian asked about this before. All right? So it's still negative 784. It's not like he suddenly loses weight when he goes skydiving. That'd be like the coolest diet program ever, right? I'll just go skydiving. I'll lose weight. All right, everybody good? All right, so what does this do to his net force, you guys? Is it still going to be 784? No, it's going to be less, right? So negative 784 plus 144, it gives you 640 newtons, negative style. And so now I can find my acceleration by doing net force over mass, and you get negative 8 meters per second squared. Let me write out where I got the negative 8, just in case anybody's embarrassed to ask. So we got net force over mass. So negative 640 newtons was our net force. Mass is 80 kilograms. Divide this and you get negative 8 meters per second squared. All right, problems with what I just did there? Everybody good? All right, so let's be clear here. So in drawing A, there's no air resistance. And so his acceleration is negative 9.8 meters per second squared, right? In drawing B, we do have air resistance, and so his acceleration is just negative 8 meters per second squared, right? So true or false? He's moving slower in drawing B than he is in drawing A. We got one vote for false. What do you guys think? The acceleration's less, right? Does that mean he's moving slower? No. The idea is, as you fall, you speed up, right? So the reason this air resistance is bigger than this air resistance is because he's moving faster here. So now I'm confused then. This is less than this, though. How can we be moving faster over here? What's the significance of the fact that the 8 is smaller than the 9.8? It's not telling us that we're moving slower. It's telling us that we're accelerating more slowly. We're gaining speed more gradually. So here, we're going to gain speed super quickly because the acceleration is almost negative 10, right? Here, we're going to keep gaining speed pretty quickly, but not as fast as we were over here. This is super important. If you've zoned out, that's a really big idea here. Moving faster here, because it took time to get to this point where our air resistance is bigger. But because air resistance is bigger, we're going to keep gaining speed, but at a slower rate. Questions? Yeah, Alex?
Is there a way to calculate the rate at which you...
Ish, and we do a little bit of that in AP. It's very, very complicated. So, because it depends on your speed, you know what I mean? So, all right, everybody good up to here? All right, so a minute later, is he going to be going fast? So in this drawing, I think he was moving down. I should have drawn this. He's moving down at 27 meters a second, right? I think that was what the problem told you in part B. So a few seconds later, is he going to be going faster or slower than 27? Faster, right? Because he's still accelerating downwards. All right, so question C says, all right, oops, I wanted that to be a different color. Question C says, a little while later, he's moving down at a velocity of 50 meters a second. And now the force of air resistance is 384? But my gravity is still the same, which means my net force now is just negative 400 newtons. So if you calculate the acceleration, you get negative 5 meters a second squared. So we're still gaining speed downwards, but even more gradually than we were before, right? Am I making sense? Any problems? Matt, how you doing over there? You doing all right? You good? Suzanne, how about you? Good. Charles, good. Cool. Okay, you good? Everybody's happy? Okay. So we're going to keep speeding up. So a little bit later, we're going to be going faster. So when you get to D, see if I can squeeze D in here real quick. So in part D, now our force of air resistance is it 724? 720? Force of gravity is still negative 784. The velocity here is negative 53 meters a second, I think. And so your acceleration here ends up being negative 0.8 meters per second squared. All right, so the calculations for B, C, and D are all exactly the same. It's just different numbers, right? So that's why I'm getting a little more hand wavy here. So if you're like, how the hell did he just do that? The calculations for D are literally the same as B. All right, so are we good up to there? All right, so what's the point? Like, why am I spending all this time on this? What's going to happen? So what have we decided? So when you first jump out of the plane, you gain speed very quickly. As you gain speed, your air resistance gets bigger, causing you to continue gaining speed, but not as quickly. But since you're still gaining speed, your air resistance is going to get bigger. So you still gain speed, but not as quickly. But the point is you continue to gain speed, but more and more gradually. Eventually, what important thing happens, you guys? You stop accelerating, right? Because eventually you're going to be going fast enough. Eventually you're going to be going so fast that gravity is pulling you down, but now you're going so fast that the air resistance exactly cancels that out. So now what's my net force, you guys? 0, which means my acceleration is 0. Does that mean I've stopped moving? No, it means I've stopped accelerating, right? Now, in this problem, it tells you that that happens at a velocity of 55 meters a second. That's specific to this problem. That is not every object in the universe. Okay? Good. So, oh, darn it, stupid smartboard. All right, so the velocity at which the force of air resistance is equal to but opposite the force of gravity is called terminal velocity. All right, and calculating this is very complicated, so we will not be doing that. But the moral of the story is if I give you a problem and I say, Roy drops a bowling ball off the Empire State Building, make a free body diagram, what's its at terminal velocity? You just ensure that your air resistance cancels out your gravity. All right? Now, what is the terminal velocity? Again, it varies from object to object, which is why this piece of paper is not very heavy, so there's not much force of gravity. Okay, and it's got a large surface area, so it doesn't have to be moving that fast to catch air, and as a result, it falls almost at a constant velocity, right? The only reason it's not perfect is as it falls, it flutters and it tips, and that changes the way the air resistance affects it. Okay, so this has a very small terminal velocity, but if I change the shape of it, now it has a higher terminal velocity because it catches less air. It's got to be moving faster in order for the air resistance to cancel the gravity. Good? Questions? All right. So, that's the end of 16, but we're not done. I'm sorry. Poof! Parachute! So here we go. F. Roy's like, oh crap, I have just jumped out of a hovering helicopter and the ground is approaching quickly, so he opens his parachute. So here's Roy. Gravity is still pulling him down with negative 784 newtons. Poof! Parachute Parachute! Did not give myself enough room. All right. So what's the point of the parachute, guys? What is it? Oh, well, hold on. So to be clear, right now he's moving down still at 55 meters a second, right? Because he just jumped out of a helicopter and he's falling down. Poof, parachute. What does the parachute do, you guys? Sure, we got Anders. How does it increase the air resistance? You're right. Why? That's exactly what I was looking for. It's more surface area, right? You're taking your parachute, which is all bundled up in your backpack, and then you're going poof, poof, right? So you're going from this to this, right? So the idea is you're moving very quickly with your parachute open. It's going to catch a lot of air, resulting in a tremendous amount of air resistance. So maybe it's, I'm going to make up a number. There's a ridiculously large number just because it'll make the math easy. All right, so what does this make my net force, you guys? Well, I got 1,784 up, but only 784 down, so the net force is just 1,000 newtons, right? Follow? So now I can find my acceleration. It's going to be net force over mass. Oh, positive. That's the whole point of this. All right. So he's moving down, but the acceleration is up. What's he going to do? It's going to slow down, isn't it? Does that mean he's moving up? No, it means he's moving down at a decreasing rate now, right? Because now the net force is working against him. So a moment later, he's going to be falling down again. So here he is again. Oh, we're still doing blue apparently. Force of gravity is still negative 784, but now he's moving slower. So now maybe he's going at, I don't know, 40 meters a second. His parachute's still open though. So what's the parachute doing? Still pushing him up with a force of, I don't know, let's say 1184 newtons or whatever. You guys see what's happening? Right? So this makes the net force positive 400 newtons, which makes the acceleration positive 5 meters a second squared. He's still going to slow down again, right? And as he goes slower and slower, the air resistance gets smaller and smaller until eventually, hopefully before he hits the ground, the acceleration gets back to zero again, right? Does that make sense? So the whole point of the parachute is, over time, it makes you go from this velocity, poof, eventually to that velocity. But it takes time for you to slow down from this to this. Make sense? Questions? There's a lot going on here. Questions with it? All right then. I think I'm done. So, I'm going to give you a target check. If you finish it, cool. If not, it goes in your folder and then comes out of your folder again tomorrow when you get back to class. Hello. How are you? I'm sorry my cabinet doors attacked you because Mr. Hernandez didn't close them. Hernandez. Ooh, I have her. I will give this to her. Oh, you're very welcome. Oh, what you're doing. Thank you. I appreciate your help. 1, 2, 3, 4. Ooh, I like 8 plus. Did my message last night make sense?
Yeah.
Sorry about the costume. I'm crabby about that. And special delivery. There is one little typo. Most people have been able to figure it out, but just in case, flip it over on the back. question C says for each set of parentheses, blah, 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 and then there's 3 bullet points. And then at the end of each of the 3 bullet points, it says it was in part C. That's supposed to say part B. Okey-doke, off you go. When you're done, throw it in the basket. If you don't finish, throw it in your folder. And I will see you tomorrow. Ooh, we need to stop the recording, and then let's talk when you get back.